Hi guys, I'm sorry I wasn't in class today to present this to you in person. I was going through some stuff and Mr. B gave me permission to make a screencast of my presentation instead, so I hope you all enjoy it. My presentation is about radiation from the stars. First I'm going to start with talking about black bodies. A black body, as you all know, absorbs radiation. And a large cavity, for example, with a small hole in it will be a black body. All of the stars in the sky that we see are basically all black bodies. For example, the sun is a black body. And these black bodies emit black body radiation, which is what we see from far away. So from Earth, the colors of the stars that we see from far away are determined by blackbody radiation and their wavelengths and frequencies. So, scientists for many years have been endeavoring to create laws and equations that will explain what kind of wavelengths and frequency determines what color these stars are perceived as from people on Earth. The first law that was proposed was Rayleigh-Jean's law. It was proposed in the late 19th century. The equation is a pi kt over lambda to the fourth. T is in kelvins, and K is the Boltzmann's constant in joule seconds. The second law proposed was Planck's law. It was discovered in 1900 by a man called Max Planck. His equation was a pi hc lambda to the negative fifth over e to the hc over lambda kt minus 1. Also for this equation, T is in kelvins, H is the Planck's constant in joule seconds, C is speed of light, and K is the Boltzmann's constant in joule seconds. So, both of these laws were basically proposed at around the same period of time, but scientists, after doing many experiments, discovered a fault in Rayleigh-Jean's law in the case of short wavelengths. So, in his equation, this law said that the equation a pi kt over lambda to the fourth, as lambda goes to 0 from the right side, f lambda goes to infinity. However, experiments have shown that as lambda goes to 0 from the right, f lambda in fact goes towards 0. This proved Rayleigh-Jean's law false in the case of short wavelengths. So, in contrast, Planck's law for short wavelengths showed that as lambda goes to 0 from the right, f lambda also goes to 0. So it better represented blackbody radiation in short wavelengths with the equation of a pi hc lambda to the negative fifth over e to the hc over lambda kt minus 1, because losing L'Hopital's rule, we can determine that as limit of f lambda as lambda goes to 0 and limit of f lambda as lambda goes to infinity both equal 0. So this is better depicted in this graph. As you can see, this is the Rayleigh-Jean's law, and this is Planck's radiation formula. Rayleigh-Jean's law, as we just discovered, as lambda goes to 0, f lambda goes to infinity, which is also commonly known as the ultraviolet catastrophe. And in contrast, Planck's law forms a nice curve to show that as lambda goes towards 0, f lambda also goes towards 0, passing by the visible spectrum of the electromagnetic spectrum. But you can see that for short wavelengths, the two laws differ drastically. But for long wavelengths, as you go towards infinity, they seem to converge towards the same point. And scientists and mathematicians have discovered that this is in fact true. We can prove this true in the cases of long wavelengths by using Taylor polynomials for Planck's law. So the Taylor polynomial equation for e to the x is 1 plus x squared over e to the e factorial plus x to the third over 3 factorial, and so on. And the Taylor polynomial for e to the hc over lambda kt, which is the version of e to the nth power used in Planck's law's equation, is as follows. So basically the sum of e to the hc over lambda kt, you can say that it is 1 plus hc lambda kt. So if we use this and do several equations, you can tell that Planck's original equation, a pi hc lambda to the negative fifth over e to the hc lambda kt minus 1 will equal the sum of the Taylor polynomial minus 1 in the denominator. And if you take it a step farther, it will become this. And then if you do final equations, we can determine that Planck's law basically converges to an equal constant as 8 pi lambda to the negative fourth kt, which is the Rayleigh-Jeans law. So these equations show, using Taylor polynomials, that as lambda goes to infinity, both laws approach 0. So we just graphed both of these graphs, and for Planck's law, you can see we're going to look at Planck's law's graph in more detail in the case of certain temperatures. For example, the temperature of the sun is known as 5,700 K, and if you look at this graph again, this is a graph for 5,000 K in the case of Planck's radiation formula, which is basically roughly similar to the sun's radiation. And you can see that the maximum point of this passes by the white region of the visible spectrum, which is why we perceive the sun as white from Earth. And the graph obviously varies in coordination to t. For example, like if t is 3,400 K, it passes by a different maximum point, changing the color of the star. The total emission is the area under the curve. And we're going to look at specific examples of star Betelgeuse and star Sirius. Betelgeuse is known as the red star, as you can see here, and Sirius is known as the blue star. If you look at the graphs of roughly these wavelengths, these temperatures, first, the red star Betelgeuse, the temperature is roughly equal to 4,000 K, and you can see that the maximum point is roughly at the point of the red and orange area of the visible spectrum. This is why we see the star as red. And the wavelengths of Sirius at 7,000 K passes by the purple and bluish area. The maximum point passes by the purplish and bluish area, which coincide with the wavelengths of purple and blue. So we can determine that Sirius is blue. And as we said before, the white star is our sun because 5,270 K, similar to 5,700 K, passes by the white region. So this is how we determine the color of stars. Planck's law proved to be a reasonable and realistically accurate version of rendering the black body radiation of stars according to wavelengths and temperature. And using this law's graph, we can graph the equation at different points using different temperatures, and this makes the graph pass by maximum points coinciding with the wavelengths of the colors in the visible spectrum, which is pretty interesting. Okay, so I hope you guys enjoyed my presentation, and I'm sorry again that I wasn't in class today for this.